cook up two different bases for this, then what can we say about them? Then B1 and B2 have the same number of elements. If you recall, this sort of absolute value symbol around the set means how many things does it have in it. So the two bases will always have the same number of elements. And this is actually a really straightforward consequence of this theorem right here. So what happens if B1 has more elements than B2? Well, B2 is a basis, so it's linearly independent. The vectors are linearly independent. If this has more vectors, sorry, I got that backwards. This is a basis. If this one is also a basis, then the elements are linearly independent. But there's more of them than there are here, so it must be linearly dependent. So this one can't be bigger than this one. And now we just swap 1 and 2 and do the exact same proof. So they must have the same size. I'm going to write this again. And then the size of B1 equals the size of B2 equals n. And the vector space V is said to be n dimensional. Or another way we can write this, the dimension of V equals n. So although the coordinate mapping that we actually get does depend on what basis we choose, the dimension of the space does not. The dimension that we get is, of course, the same as the n that we get after the coordinate mapping. So we map into Rn. So this is an intrinsic property of the vector space, right? It has nothing to do with the basis itself. It's a property of the vector space that doesn't depend on the basis. Now, suppose that no finite set spans V. So if we keep looking for vectors and adding them into our spanning set, and we keep getting something that's smaller than the actual vector space that we're trying to span, then V is said to be infinite. Infinite dimensional vector space. Anybody think of an example of an infinite dimensional vector space? So we've seen one before in our examples. R is actually a one-dimensional vector space. So we can get a coordinate mapping for R. It would just be the number itself. So for example, a spanning set for R would be 1, the number 1. Because we can get everything else by scalar multiplication. Any other guesses? I'll let you think about that for just a second, and I'll come back to it after I do some more examples. So let's look at R3. This is the three-dimensional space that we're familiar with, from not only from calculus 3, but also real life. How can we characterize the subspace of this? Well, we know that if we have any set of vectors from this, if there's more than 3 of them, it's linearly dependent. So the spanning sets have 0 vectors, 1 vector, 2 vectors, or 3 vectors. So if the dimension of the subspace is 3, then H is all of R3. Right? 3 linearly independent vectors span R3. This is something that we got from the invertible matrix. If the dimension of the subspace is 2, so we get 2 linearly independent vectors, what do we get? Not R2. No, because we're looking at subspaces of R3. Things in R2 have 2 entries, things in R3 have 3. We're close. It's isomorphic to R2. But it's a different language for describing this one. Exactly. I was actually pointing at you because I knew you were going to get this one. So the dimension, if the dimension is 2, we have 2 vectors. They have to go through the origin, and they span some kind of plane. So these are planes that pass through the origin. I'm just going to put an O. If the dimension is 1, so if we have 1 vector, what does that span? It's a line, yeah. What kind of line, though? Yeah, it has to go through the origin, remember? So we always have the linear complement. Well, in any basis, we always have the 0 vector. In any vector space, we always have the 0 vector. So that's going through the origin. So we always have that point. The question is, what are the other ones? So these are, well, I'm not going to write it. These are lines that pass through the origin. And then dimension H equals 0. This is just the 0 set. It's the set with just 1 element in it, and that's the origin. It's the 0. Okay. So we can find lots of, for example, in the dimension equals 2, we can find lots of subsets of R3 that are isomorphic to R2. We can take that plane that goes to the origin and rotate it any way, as long as that point, it sticks to that point of the origin. That's one point in the plane. Okay, so back to this example of an infinite dimensional vector space. Anybody come up with one? So if you remember, we had, for example, P3. So this was a basis for this was 1x squared x cubed. This tells us, first of all, that it's a 4-dimensional vector space, right? So the basis has 4 elements. If we went to P4, then we have 5 elements. We have a 5-dimensional vector space. And in general, the dimension of Pn is equal to Pn plus 1. What about the vector space of all polynomials, just P? What's the basis for this? Was that?
From like 1 to infinity?
If you mean the exponents on the x's, then yeah. Yeah, so we have 1 x squared, x cubed. Well, we can keep going like this and we never get to a basis. We have a finite number of things. If we kind of stretch our imagination a little bit and think about an infinite set possibly being a basis, then we get this one. It just goes on forever. The book sidesteps questions like this. We only talk about finite basis, a finite basis. There's a reason for that. it sidesteps this weird question. What if we allowed an infinite number of elements and then we talked about linear combinations of those? We never talked about the fact that we could have a weight on every single element. That was okay in the finite dimensional vector space, right? We knew how to add a finite number of things. We could possibly end up with an infinite number of things in a sum here. And so one example we might end up with is, the one I'm thinking of, 1 minus x squared over 2 plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. And the pattern continues like that. Anybody know what this is? I'm not going to waste too much time on this. This is cosine of x. Unless I screwed up. I think I got it right. So this is cosine of x, which is definitely not a polynomial. So when we have an infinite basis, we have to add the constraint that we only look at finite sums, finite linear combinations, and then we're okay. But the book, like I said, it sidesteps this issue. Okay. Run out of time. Talk faster. So, if we, how does the book say this? I'm going to say it in the same way. It's not too bad. So if H is a subspace, yeah, let's say that H suppose that H is a subspace of V, a null space, for example, or the column space. Okay, so I should say the kernel or the range, because we didn't talk about what the dimension of V was. So if H is a subspace of V, then we can say that the dimension of H is less than or equal to the dimension of V. At this point, I believe the book probably says that if V is finite dimensional, to avoid the kind of weird complications of saying that a number is less than or equal to infinity. I think we're okay with that, though. So if H is a subspace of V, then we have that the dimension of H is smaller than the dimension of V, or could possibly be equal. And any linearly independent set of vectors from H can be expanded to a, my handwriting is terrible here, to a basis of H. Okay? Yes?
Sorry, it's okay if I ask a question about a little bit earlier on.
Yeah, totally.
Talking about two-dimensional space in R3,
Yes.
or subspace in R3.
Mm-hmm.
That would also include any line not going through the board, correct? Because that effectively acts as just a single part of the line going through the origin.
If we're talking about subspaces, then no. Because a line that doesn't go through the origin doesn't contain 0. It doesn't contain the origin. And every vector space contains the origin. Now, we might talk about subsets of a vector space, but that's not a subspace.
Okay, so
Right.
it's a subset of those things, sorry.
Yep.
So you're, by expanded, you mean by adding in a couple of more entries, right, to the...
Yeah, well, I think this is the same way they phrase it in the book, but
No, I was just,
that's exactly how I'm gonna do it.
okay.
Right? Okay, so just a quick explanation, more thorough in the book. The dimension of the subspace is no greater than the dimension of the vector space. How can we say that? Well, we get a basis for this. If it has more vectors in it than the basis for V, then, well, everything that's in H is also in V, right? It's a subset. So if we have a set that has more elements than the number of elements in a basis for V, then it has to be linearly dependent. And so it can't be a basis. So it can't be any bigger than the basis for V. So has to be the same size or smaller. So that establishes this inequality. So just like over here when we were looking at the subspaces of R3, we looked at the dimension of 3, 2, 1, and 0. Same thing works in general. Any linearly independent set of vectors from H can be expanded to a basis of H. How does this work? Well, if we have a set of vectors that spans H, and they're linearly independent, we're done. We have a basis. So assume that it doesn't span H, and there's something in H that's not in the span, throw that in. Because it was linearly independent before, it's linearly independent after because that thing wasn't in the span. If it was in the span, it would have been linearly independent. Keep doing that until you have a basis. That's it. Oh, as long as, yeah, I have to say, if dimension of H is finite. Eventually it has to stop. If this goes on forever, well then you know it's infinite dimensional. Okay. So suppose that the dimension of a vector space is equal to n, then a set of n So if let's take a collection of elements from V. So n of them, V1 up to Vn. I'm going to call this V. Implying that let's call it A. I don't want. I'm trying to get to the point that it's a basis. I'm not starting out with a basis. So I picked n elements from V. If A is linearly independent, then A is a basis. Okay. And if the span of A equals V, then A is a basis. Okay. How can we show this? Well, we know that the dimension of V is n, the basis has to have n elements. So, if, let's say, A is linearly independent, then because there are n of them, it has to span the space. Right? We can translate this into a question about Rn and show that n linearly independent vectors spans the space, and then switch back to V. Same thing here, if A spans V, and there's only n of them, then they must be linearly independent and therefore a basis. Same type of thing. We switch it into the language of Rn, and we switch back. Okay. Now the final thing is we can look at the dimensions of null A and the dimensions of column A. So column A, in this case we're talking about a matrix A, right? So in this case we're talking about Rn. So the call space of A, we can get that by doing a row reduction to figure out where the pivots are. So those will be the columns that span the column space from the original matrix before it was reduced. You just look at the ones with pivots. So the number of vectors that span that are just the number of pivot columns. So dimension of column space is the number of pivots. Now, if we do the same row reduction with the augmented matrix, AX equals 0, so there's a 0 column. You know, spend all this time like switching all the directions so that I know that this goes to right for you, but it's to left for me. and then I started teaching on Zoom, and you don't have to switch it. So now I'm confused every time I do it. I'm like, am I doing it the right direction or not? So dimension of the null space of A, we might think that we have to do all that work, but what we actually find is that when we do the row reduction, we also get the number of free variables as well. Those will be the columns that span the null space. And so the dimension of null A is equal to free variables. So you know a column is either going to correspond to a free variable or to a pivot, right? So we add these two things up, we get the number of columns in one trace.
So for that last one,
Yeah.
when you say if for a subspace it can be expanded to be a basis, it works the other way, right? If you have a vector space, its basis can be like diminished to be a basis.
Yeah, actually, any set that spans, yeah, we can go in the opposite direction. That was the, there was a name. Dropping the vectors theorem.
Mhm.
Yeah. So by the dropping the vectors theorem, we can take anything that spans H, drop anything that's linearly dependent, it still spans the same space. So we just keep doing that until it's linearly independent, and that gives us the dimension of range. As long as it's a finite set so that we can eventually get to a stopping point. Speaking of stopping points,